Thank you, Traversals, for pointing that out. The AO link was busted. Forgot to announce this in the previous section, but every programming test, including the application objective tests, it's all released. It's all out there. So knock yourselves out if you're up to date on all the tests, which unfortunately is very few of you. You can brush through the rest of the course if you want in terms of programming tests. And of course, the quizzes and interviews, you got to wait for them to come around in lab. But all the programming tests are released, so you can see at least what you're expected to do for the rest of the semester in terms of programming. This week, we're going to start trees. This is kind of a refresher of where we're at in the structure of the course. Roughly each week corresponds to a programming test. So last week, before the break is a void in my mind, was programming test 4. So I'm done talking about everything from programming test 1 to 4, all the content's out there. That's all in your hands at this point. And I'm starting programming test 5, talking about trees. As we're going to start talking about today, we got a week of binary trees to talk about. Lab this week. Question? Okay. Lab this week is the second chance quiz and interview 1. I always get lots of questions about this, so I want to make sure I address everything in lecture so I can get ahead of all of your questions. Quiz 1 and interview 1, second chance. We had the first chance interview last week, first chance quiz 2 weeks ago. The grades are posted for all of them. We had, I apologize again, we had some confusion, a little disconnect between me and the TAs. We're changing the way the grading for quizzes works, and I just didn't communicate very well how the grading was changing. But we got all the regrades done. So interview 1 and quiz 1, they're posted on Autolab. Double check your scores to see what you have. All the quiz regrading, it's all done. We reviewed everything and looked them all. But double check your scores for those. And if you have credit for quiz 1 and interview 1, meaning in Autolab, your score says 1, which means you've completed that learning objective. If you have credit for both of them, you should not show up to lab this week. There's nothing there for you. Nothing to do in lab if you already have credit for quiz 1 and interview 1. There's no reason for you to be there. Unless you want extra practice, you can take the quiz, I suppose. But the TAs won't call your name for the interview. You won't be able to do the interview. But if for whatever reason, and very few students have ever done this, which I understand, take the quiz 1 again for extra practice. We're not going to stop you, but very few students actually do that. No reason for you to be there if you have credit for both of them. Yeah?
Do you have to retake all the questions again, or is it just the...
It's all the questions. Yeah, if you're retaking the quiz, you have to do all 3 questions again. Yes. But if you have credit for one or the other of these, you only do the one you don't have credit for. So if you pass the interview but not the quiz, you come to lab and you just do the quiz. You do not do the interview again. If you pass the quiz but not the interview, you show up just to do the interview. You don't have to do both of them. But yeah, if it's the interview, you have to redo all questions on the interview. If it's the quiz, you have to redo all questions of the quiz. If you're in the latter situation where you need to redo the interview, but you already have credit for the quiz, you can politely ask your TA to explain the situation and ask your TA if you can be one of the first interviews, that they should accommodate you and get you in and out quicker because you're just sitting there waiting for your interview. Those of you who have to do the quiz and interview, you have to be there anyway doing the quiz. So somebody who's just there to do the interview, we have this opportunity to prioritize you and get you in and out quicker so you're not sitting there waiting for an hour to just do your interview. For the first round interviews, everyone has to wait. Like everyone's only there for the interview. Logistically, we kind of have to make you wait. But for the second chance, we have an opportunity to prioritize you, so why not? The TA should be happy to accommodate you on that one. If they're not, let me know. I'll have to yell at a TA. Like, they should be reasonable. Are they the same questions? Does quiz come before the interview? The quiz, oh yeah, we haven't had this situation. We used to always do quizzes and interviews simultaneously. So I guess this is the first time it comes up. You're going to show up and do the quiz. For the case where you have to do both, you're going to show up. It'll be just like a quiz lab. They're going to give you the quiz link. You're going to do the quiz. You're going to be sitting there cranking out the quiz. And while you're doing the quiz, simultaneously, they're going to call you for interviews. So everybody fires up the quiz, and the TAs will start calling out names for interviews, which isn't ideal. That you do have to be distracted, pulled away from the quiz to do the interview, and then get back to your quiz and remember where you were. It's not ideal. That's why I don't like to do it. I got it down to just the second chance labs where we're doing it that way. It used to be everything. It was always a quiz and interview at the same time, so it's better than it used to be. But if you failed both of them the first chance, unfortunately, logistically, we got to do them at the same time. Either that or we would have to cut your quiz down to, like, limit you to an hour, which would still be fair, I think, but we're going to give you the full time and have you distracted by the interview. Yeah.
So I passed the quiz and I came there on the interview. I came there on time, but it's just penalty they did of 2.
On the interviews, the penalty late days. When you see these in Autolab, you can ignore them completely. There's no concept of penalty late days in this course. But Autolab is set up to always think in terms of penalty late days. I wish I could just delete that column and say this course doesn't use penalty late days. All that means is the TAs uploaded the grades for the interview you're talking. That means the TAs uploaded your grade 2 days after whatever they set for the deadline, which there is no deadline. Like, you do it in lab. So it's just a logistical thing. You know what? I can fix that right now, actually. And those, at least for the interview, the penalty late day should go away with that, just by setting the deadline later. Good. Because even though it doesn't mean anything, it can still be frustrating seeing penalty late day too. And I think that's all the logistics I wanted to talk about there. Yeah.
So we only got 2 more quizzes and interviews left, right?
Yeah.
After this one.
Mm-hmm. Yeah, there's only 3 total this semester. There used to be 6, and it was a lot. It was a lot it was a lot for you to take. It was a lot for the TAs to grade. It was a lot for Paul and I to manage on the gradebook side. It was just a lot. So linked lists and trees used to be separate. I combined those. Inheritance and polymorphism used to be separate. I combined those because they're really the same concepts. Node-based data structure and OOP. And then we used to have a graphs quiz and interview, and I just cut that one completely. So graphs are only going to be programming tasks, which I think so far I think it's working, where things just flow a lot better. Plus, I think it's easier to prepare. Hopefully, some of you can back me up on this. But I think it's easier to prepare when you have 3 things to focus on instead of 6, and you can kind of multiply those by 2 since there's quiz and interview. When there's 12 total, 6 interviews and 6 quizzes, it was just chaotic. Every week was a new quiz and interview. And programming task. It was just so much. And we're assessing the same thing. I'm still assessing the same thing. We just have fewer, larger quizzes and interviews. Will the quiz questions be easier compared to the first time or difficult? They won't be easier. They won't be more difficult either. It's always up for debate, I guess. Everybody's going to think something different on this, but there's no intentional increase or decrease in difficulty from the first to second chance. I want the difficulty to be at the level where we're assessing whether you understand the concepts or not, and that's it. There's no reason to go above or below that. But below that, then the course isn't testing. You're getting away without knowing what you're supposed to know. But anything above that is just, I never see a reason to. If you understand the concept, you can do something more difficult, which doesn't really happen in practice. But since I already dug myself into this explanation, I'll finish it off. If you can understand the concept and do an easy question, you can do an extremely difficult question too. If I just throw more constructors and constructor calls inside constructor calls inside a recursive method, you can do that, but it increases your chances of making a mistake. Even though you understand the concept, you're going to somewhere in there make some mistake that's going to blow up your whole memory diagram. And I don't like that feature where you can understand the concepts that I need you to understand, but still get the quiz wrong. So I try to get it just at the difficulty where it's assessing what you need to know without being tedious. And a few of the questions missed that a little bit, in my opinion. But overall, I try to keep that limited. Limit the tedium. So questions were looked over again automatically. Yes, I looked over 120 quizzes painstakingly. It sucked, but it needed to be done. Also, will we ever get the answers to the quiz? No, I don't intend to release solutions, but if you go to office hours, I'd be happy. Me and the TAs would always be happy to talk over them with you, but I'm not going to release electronic solutions. What were the changes to the grading requirements to quizzes? I got to start lecture soon. I can't go over everything, but roughly what I just said, taking that and then trying to get that into a grading rubric. The short answer to that is if you made any mistakes that are fundamental to what I'm teaching in 116, which is references, classes, objects on the heap, references on the stack, those things, any mistakes there was typically a fail on the quiz. But if you made mistakes that are related to 115 concepts, like you didn't do the loops quite right, or you missed a getter frame on the stack or something like that, those were usually overlooked. But like if you had, for example, if you had the wrong number of objects on the heap, that would be an automatic fail. Like that one's easy to take a look at and say, nope, you didn't understand objects, constructors, and references, especially when it's assigned by reference. When we create one truck, T1 equals new truck, T2 equals T1, and you got two trucks on the heap, you don't understand assigned by reference. That's easy. That's a 116 topic, 116 concept that you didn't understand. Easy fail. But you could make a lot of mistakes, and the TAs are pushing back on me about this one a little bit. Certain TAs, I won't give any names. But you can make a lot of like the 115 level mistakes. If your loop was supposed to loop 4 times and it looped 3 times or 2 times even, I want to overlook those ones. As long as your objects and references and all that was solid. But any mistakes with objects and references and constructor calls, that's because there were only 3, right? There were only 3 objects you had to create. If one of those went wrong, that blows up your whole thing. That doesn't show me that you understand references and objects and all that stuff. So the TAs graded them, and I want to clarify this, the TAs graded them properly according to the way we have been grading them over the years. This is something where I'm enacting a change. I want to change the way we grade them by waiving. We didn't used to waive all those things. Like there are some really crappy submissions that I gave credit to, let's be honest. And those usually would not get credit, but I'm making the change to waive a lot of those little things that aren't related to 116 specific topics. That are more 115 topics, which is controversial. Like, if you really don't understand those 115 topics, you should be failing. But I am making the decision to, on the quizzes, give you credit. So the TAs are adjusting to that. We're having meetings and talking about it and talking about what that should look like and everything. So they didn't misgrade. It's just I didn't communicate very well to them exactly how much should be overlooked as long as you have the 116 concepts solid. Yes?
And those small mistakes that you're saying are going to be like overlooked, they would still put in the feedback or no?
Yes. Yeah, so those mistakes still go in your feedback. So some of you had feedback that had a laundry list of like 15 things that were wrong, and then you have a 1 for your score. You still got the learning objective. You should still take that feedback and address that in the next quiz. You should still fix those mistakes that you made. I'm just saying they weren't so dire that I would say you can't go on to 220, 250 with these mistakes. That's effectively what I want the grading to be. And the grading used to, I got to cap off this conversation because we got to talk about trees, but there used to be 2 thresholds for quizzes, one to pass the learning objective and another where if you did like really well, you would get an application objective on the quiz, where that switched to if you get it the first try, you get the application objectives. Second try, you get 1 of them. So the grading is just different. It's just took us a quiz to adjust to it, you know. But the TAs are on board now on seeing my vision and everything for that. So I don't foresee it being an issue on quiz 2 or 3, or the makeup quiz 1. But all those small mistakes, y'all should tighten it up, seriously. It's just not like before we could have that lower threshold be, at the level of where it is now. And then we'd say, okay, but you don't get the application objective. But now we don't have that second threshold. So it's weird just having this lower one where if you really knock it out of the park, you don't get rewarded. So that, I'm not super thrilled about that, but I think this is the way to grade quizzes moving forward. I just don't like seeing people lose credit because of silly mistakes, like missing an iteration of a loop. I don't think any of you missed an iteration of a loop because you don't understand loops. I think you just made a simple mistake. You thought it was less than instead of less than or equal, something like that. Like, I don't think that's dire enough that you should fail the course. But we had on Q3 a situation like that where we were making method calls inside a loop. So now the TAs are seeing that you're missing stack frames, you're missing entire method calls. But really the fundamental mistake was you just missed one iteration of your loop, but it cascaded into missing, I don't know. I got to talk about trees, but if you come to office hours, I'll be happy to talk about it forever. If you still aren't thrilled about your quiz results, come talk to me in office hours. I'll be happy to talk about your quiz specifically also and explain the grading more. But we got to talk about trees. That was way too long. All right. The TLDR of that is quiz grading got softer, and it's probably a little too soft, but I think this is where it should be. When it's pass fail, I think this is where it should be. But all right, so binary trees. This is another node-based data structure that's going to store our data in a different way. And they're very similar to linked lists, also node-based data structure. With linked lists, we had each node containing the value for that node and a reference to the next node in the linked list. Trees, binary trees, are very similar. They're going to be nodes that contain a value, the value for that node, except they're going to have references to two other nodes. And that's the difference. You now all know trees. There's a reference to two nodes instead of one. That is the structure of a tree. That really is it. What we have to talk about the rest of the week is the implications of this and rewriting our algorithms to work with this new structure. We call these references, instead of next, as it was with linked list, left and right. And we usually call them child nodes, a left child and a right child. And to that child, that node is going to be the parent node. And if you study trees more, when you get to 250 and 331 and beyond, this analogy really extends a lot further. Parent and child are the only two we're going to use in this class, and usually child over parent is more useful for the explanations I have to do. But this does extend grandchild, grandparent, aunts, uncles, ancestors, descendants. All that terminology is part of the analogy. There's also a simultaneous analogy to trees from nature. We're going to see the root of a tree. I'll mention, I don't have it defined on a slide anywhere, but branches, leaves, two simultaneous analogies for these things, which, it is what it is. And here's an example of a tree. Instead of our linked list nodes, where we just have next, 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 next until we reach null, and then null is when we have the end of the list. Trees are going to have the value and then a left and right child, which can be null. We can have nulls here, meaning that there is no child node there. It's the lack of a reference. And this is the tree that I'll use for most of the lecture examples because it's nice and pretty, I think. It's a symmetrical tree. We have everything what we call fully balanced on this tree. Makes it nice and symmetrical. Looks pretty on a slide. But this isn't how it has to be. We can have all four cases. We can have left and right both being null. We can have left being null, but right being a reference to a node. We can have right being null and left being a reference to the node. Or we can have left and right both being references to nodes. All four cases are valid. I like saying this right up front because I used to see a lot of mistakes in homework until I added the slide and explained it. A lot of mistakes on homework where students would say, if left equals null, assume right is also null, or vice versa. Assume left has a node, or if left has a node, if left is not null, then assume that right is also not null and start traversing the right child as well, which is going to get a null pointer exception. Or in the first case, it's going to miss part of the tree. So make sure you have all cases addressed. Left and right, any mix of null and not null are all valid. But for the lecture, I'm going to have a nice balanced tree just so the slides look pretty. And here's the code for this. Our binary tree node class is actually pretty straightforward. We have value and references to 2 nodes instead of just 1 like we had for linked list, and a constructor to set those 3 instance variables. And that's it. Aside from the getters and setters, which are omitted for the slide, that's it. That's our whole class. Unlike the linked list node class, where we added a lot of methods to the linked list node class itself, this is the entire binary tree node class. We're not going to add to this at all. Whenever we work with binary trees, we're going to do it in other classes. We're going to import and just use this class. To create our trees, at least for now, on Wednesday this will change. When we have BSTs, we'll actually write an insert method. But for now, we're going to manually create our binary trees, where we'll create a node to be the root node. That's part of the terminology. We had the head of a linked list was a reference to the first node in a linked list. The root of a binary tree is going to be a reference to that first node in the binary tree, which it's the root. The analogy breaks down here. It's the root. So you would think of it being on the bottom of the tree, but we flip the tree upside down and the root is at the top. So our trees are upside down, but the root's at the top, and then the descendants go down. And then we're going to manually set the nodes for left and right children all the way down the node, or all the way down the tree. And this code here is going to build that same exact tree that we had on the previous slide. It's going to build this tree. We have the root node having the value 5. We have a root node with 5. And we'll set the root.left equal to a node with 2. So root.left equals a new node. And we're manually setting the left and right nodes for each child. The root.left.right equals a node with the value 4. Root.left.right equals a node with the value 4. So we're building that same exact tree that we saw on the previous slide with this code. And I kind of mangled it a little bit for the slide, but this code is in a main method in the binary tree node class, which is why I can get away with .left, .right, even though they're private instance variables. In our actual code and the homework code and other examples, that's going to be root.setLeft, root.setRight, root.getRight.setRight of the new node. So we'll have to use those getters and setters when we're not in the same class. So that's the structure of a tree. Any questions on the structure of a tree? Because I really don't have a lot to say about it. It's the implications of it that we have to spend a lot of time talking about. Yes?
Is it necessary to have just a left and right branch, or can we have more than 2 branches?
Yeah, you can have more than 2. If you want to rewrite the class, you could have an array list of binary tree nodes. You can have any number that you want. For a binary tree, that's where the binary comes from, means that we have 2 children. But you could write one. You could write a ternary tree with 3. You could write a multi-tree with any number of child nodes that you want. But the one we're specifically talking about will have 2. Yes?
I want to talk about binary traversals, but I'm not going to talk about it.
Yeah. When we get to the next slide. Do you have a question about it right away?
Oh, no, I just have
Oh, yeah. Yeah, that's the next thing we're going to do is traversals. Yep.
Can any value be stored for the tree, kind of? Like the
Mhm.
nodes? Any value still go on there?
Yep. So we still have a generic. I'm choosing integer for this one. When we get to the memory diagram, I'm going to choose string. But yeah, that could be anything. How these could be linked lists of array lists of strings. It could be anything we want. What happens if you fail second chance interview or quiz? You take it on the final. If you fail the second chance, you take it on the final to pass the class still, as your last chance to pass the class, but you can't get any AOs anymore. Oh, it was already answered in chat. What am I doing? Yeah.
Could you technically not skip past the first not left and not right by just putting the first one?
Yep. Yeah, so we could, instead of putting these nulls, because we're putting these nulls here and then immediately replacing them with actual nodes. So what we could do is take this whole thing right here and paste it right here in place of this null. Take this whole thing and paste it in place of this null. And we could actually do this all in one line. We could have one massively long line that creates this entire tree just by putting all these in place of these nulls. But I decided to create it and then replace the nulls. then replace the nulls after. Yeah, we have multiple options here. Yep.
So if you just wanted a completely null node, would you have to hit null 3 times, or would you just set it equals null?
So if we want an empty tree, we would do root equals null. Just like we did with our linked list, where we had the head of the linked list just equaling null. That would be our empty tree. If we did root equals null, 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 that's going to be a tree of size 1 with the value null, which is different than an empty tree. Yeah, the arrows on the quizzes, when I was doing the regrades, I ignored every single one of them. Nobody lost credit for arrows being jacked up or not having them at all. That's one of the things, like you should have the arrows to, and there's a lot of things like this in memory diagrams, not just the arrows, but you should have your arrows because if you do make a mistake somewhere, but your arrow is right, it's easy to tell that you made a simple mistake, and it's very easy to just overlook that. But if you don't have your arrow and you make a mistake, like you update the wrong variable and your arrow points to the right variable, I know you made a simple mistake. If you updated the wrong variable and you have no arrow, I don't know if that's a simple mistake or a fundamental misunderstanding. So having your arrows can only help you.
Yeah, I think we should also have an arrow that can go between the stack and heap just to show like the
Yeah.
the compactor.
Yes, we don't have that feature yet. Of course, I shouldn't be putting that on the quiz. Like here, I'm assigning to variables directly, instance variables directly. If I wouldn't put that on a quiz, we would use getters and setters. So we wouldn't have that case, but I still want that feature too. That came up in the other lecture as well. Yeah.
Can you use a getter to get like a particular like root left? So you wanted to get like root left. Could you use a getter to get that?
Yeah. Yeah. So when we have our getters and setters and we're using those and we want and we have only a reference to the root and we want this node, we would do .get left. So you would call it twice. You would call it to get the left node and then call get left on that left node that you got. So you can chain together method calls. Okay, so my question is, how do we work with this thing? How do we work with trees? With linked lists, things were fairly straightforward. I mean, it was still new content. We had to understand references and stuff. But I would use recursion, but a lot of y'all, from what I've seen in office hours, would use loops. You would use a loop, go to the next node, get next, until you see null. Once you see null, you're done. You're at the end of the list. As you're going through get next, you're processing each node. Can be some work depending on what you're actually doing with that stuff. Like deleting a node was tough, but like finding the average of a linked list, hopefully you didn't find that too difficult. And you just go until you find null. But how do we do that with trees? We can't just go until we find null. What are we going to do? Get left until we see null. But then when do we go and visit the right children? Like how do we just visit every single node? I say how are we going to work with this data, but let me ask a simpler question. How are we just going to visit every single node? I want code that's going to visit every single node just once. And for a memory diagram, we're going to just print the value of each node to the screen. That's all I want to do. How are we going to do that and make sure we visit every single node in the tree, so make sure we don't miss any nodes, and also make sure we don't visit any node twice? How do we visit every single node exactly one time? How are we going to write that code? And it's actually pretty simple. If you were using recursion with your linked lists, you would make the recursive call on the next node, make the recursive call on the next node until you see null. With a tree, it's the same thing. You just make 2 recursive calls, and you're done. That's it. And we're going to explore why and how that works. And we're going to see 3 different approaches, 3 different tree traversals: pre-order, in-order, and post-order. These are all going to visit every single node exactly once, but they'll visit the nodes in slightly different order. So when you're working with trees, depending on what specific application you have, why you're working with a tree in the first place, you might choose a different one of these 3. For our purposes, in-order is going to be the useful one. But pre-order and post-order, there are cases out there where people do want those traversals. And they make good interview questions. You're going to probably be asked about all 3 at some point. So in order traversal, we're going to check. We're going to call this on the root node. So starting at the root node, if the node is not null, we're going to make a recursive call to the left, calling the same method. We're going to process the node. In this one, we're effectively doing a two-string method here. We're going to process the node in question, the value of the node in question, and then make a recursive call on the right child. If the node is null, don't do anything. That's our method. Visits every node exactly once. We want to pre-order. We're going to change our code a little bit. We're going to visit the node's value and then make our two recursive calls. And for post-order, you guessed it, we're going to make the recursive calls and then visit the node in question. And this code is going to convert every value in the tree into one single string that we can happily print to the screen. That's the code for all three of them. That's it. In like 1 minute. So this code with recursion, with a linked list, we would do the same exact thing, except our recursive call would just be node.next without two recursive calls. Here we have two recursive calls, but it's pretty much the same code. We just added an extra recursive call. Recursion made this very simple. This is our first big payoff of recursion, that it made this task very simple to code. Of course, we're going to have a whole memory diagram to see why this works and explore why it works, which is more complex. But to code it, we just added an extra line, one more recursive call, and we're done. My challenge to you, those of you who are recursion naysayers, is try to write this code without recursion. A lot of you use loops to do your linked lists. You'd have a loop, get next, node equals node.getNext, well node not equal null, and then process your stuff inside the loop. A lot of you did that on the homework, which fine. I had my warnings when we did linked lists, but at this point you either heeded those warnings or you didn't. But this is where the payoff is going to be. If you got used to recursion with your linked list, moving on to trees is easy. Taking your loop code that you used with linked list and converting that to be able to work with trees, try it. Just try it. If you don't believe, it's painful. If you don't believe me, try it. Try to do any one of these traversals. You can rewrite these like we're going to do for the memory diagram and just have them print each value to the screen. You don't have to have it maintain the strings if you don't want to. But just have them print every value to the screen exactly one time without using recursion. It is difficult. If you are going to take me up on this challenge, let me explain a little bit of what recursion is doing for you. The recursion, how this makes sure. Let me just motivate what the problem even is. So you go down to like left. You can go down to the left and then the left, for example, until you reach null. That's how your loop is probably going to start. You're going to go either left or right until you reach null, and then process that node that has a left of null. But then when you start going back up the tree and starting to visit the right children for each node, how do you keep track of what nodes you've visited, what nodes you haven't visited, what nodes you visited the left child of, which nodes you visited the right child of, and just overall where you are in the whole process of visiting these nodes? The program stack and the stack of stack frames is going to keep track of all of that stuff for us with recursion. So if you don't use recursion, I recommend using your own stack. Create a stack data structure. Add your nodes to the stack to keep track of which nodes need to be processed still. And then also keep track of how much of that node has been processed. If you're doing post order, because it's the one I can reach the easiest, is this the first time I'm visiting the node? So what I'm doing to this node is making not a recursive call, but pushing the left child to that stack. Is it the second time I'm visiting this node, which means I've already processed the left child and I need to process the right child? Or is this the third time I'm visiting this node, the third time it's reached the top of the stack, and I need to process this node's value and then pop that node off of the stack, which takes quite a bit of code to keep track of all of that information, or you use the stack, the program stack, and it just does all of that. So those of you who say, which is a true statement, anything you can do with recursion, I can do with loops. That's true, but in this case, the recursion makes this way far and away simpler than using a loop. You can still do it with a loop, but you have to recreate a lot of what the stack is doing for you. And a few students did take me up on that challenge. I think I'm up to 5 students who show me working code of that over the years. It's always like 50 lines of code as opposed to 8. It's a lot more difficult. All right, and in order traversal, we're going to visit, when we get to each node, we're going to make the left recursive call first. Left recursive call, null does nothing, then visit the node. So we visit -3 first, then 2, then 4, then 5, 7, 8, 14. If we do a pre-order traversal, we're visiting the node first. So we visit 5, 2, -3, then make these recursive calls 4, 8, 7, recursive calls 14. So we get a different order depending on the traversal. And then just to wrap it up, post order, make the recursive call, visit -3 first, then 4, 2, 7, 14, 8, and then 5. So we get a different order, and depending on why you're using a binary tree in your code, in your program, one of these orders is probably going to be better than the other two. And I don't know, for my money, usually the in order. Maybe that's just the applications that I do, but in order tends to be more useful. So let's see this in action. Let's drive this home with a memory diagram so we can see this stuff in action. I'll go left, please. Do all the traversals have the same runtime? Yes. All right. So let's see this. And we're going to switch this to strings. I'm going to change it to printing to the screen instead of concatenating into one big string, just to make things a little more compact for the slide. Changing to BT node instead of binary tree node, but we're working with the same class. And I omitted the code for the class itself. Just all things to make the slide more compact, because I got a lot of information to convey. Standard memory diagram on a slide stuff. Oh, and we're doing a post-order traversal, but I just call it traversal. Again, room on the slide. So let's go through this thing. It starts off simple enough. Constructor call. Constructor is, we've been doing these for quite a while. One thing I want to remind everyone of, because I saw a lot of it going over the quizzes, if the constructor stack frame is kind of separate from the object on the heap, and what I mean by that is all the instance variables are not necessarily parameters to the constructor. Whatever constructor parameters we have, those are what go on the stack frame, just like any other method call. It's only the parameters. So if there are some instance variables that are not parameters, they don't go on the stack. I saw quite a bit of, like, if there were no parameters here, but 3 instance variables, these 3 instance variables would still show up over here, which is probably my fault because most of my lecture examples were populating all of the instance variables through the constructor. So we did see a lot of that. That was one of those mistakes that wouldn't determine your grade, wouldn't make you fail the quiz. But just to throw that out there. All right, and then the next one, this gets a little bit different. Just because we're replacing an instance variable, this is our first arrow to a variable on the heap, which again, I wouldn't put this on a quiz. We would use a setter. We would do root.setLeft, and then we wouldn't have this situation where we're directly assigning an instance variable. Constructor call, creating a node, but what's interesting is the left-hand side here, root.left. Root.left, this is the variable that we're assigning. This had the value null, but we had the value null just very temporarily. We set this null for the left child, and we're replacing the null with a reference to a new node. This is just like any other variable reassignment, but we got quite a few twists going on here. One, we're updating an instance variable on the heap, and that variable is supposed to store a reference. It didn't, so it had the value null. And now that null is being replaced with a reference to another object, whatever this constructor call evaluated to. So we're going to root.left equals replacing what was there with a reference to this new object that was created. And that's how we're formulating our trees. And I'm going to visualize the tree over here. This is the same information as what's on the heap over there. But just to visualize and see what we're working with, I'm going to visualize the tree here. You don't have to do this on the quiz, but I do recommend if you have scrap paper or ask the TA for scrap paper. Hopefully we don't run out in the lab. And I think we still have paper in there. But if we run out, I'll have to grab some. And sketch out the tree. It can help to visualize these. When you have the linked list and trees quiz, just sketching them out and being able to visualize them can be pretty helpful. But this part is not required on your quizzes. We're going to do root.right. Root.right equals a new node. And then root.right.left. A little more tricky, but the same concept. Root.right is OX480 dot left. So we're talking about this variable right here and setting it equal to a new node. And all the constructors are over. So any questions about creating the tree before we start the traversal with recursion? Okay, let's do it. All right, we're starting the traversal at the root of the tree. So our tree, what's stored in our variable, which we would think of as storing a tree, is actually just a reference to the root node of the tree. Just like a variable storing a linked list is just a reference to the first node in the linked list. So we're going to call our traversal on that root node. And this is a static method, so we don't have this in the method at all. We're just having the parameters that are passed. In a static method, we're not doing root.traversal and calling it through an object. There's nothing for this. Static methods, we don't put this in our stack frames. So node is 350. Node is not null. It's OX350. So we're going to execute the code inside the code block, which starts with a recursive call to the left. Node.left, OX200. That's going to be the node for the next recursive call. OX200 is not null. So we're going to execute the code inside the block. It starts with a recursive call, node.left. Node.left is null. So we're going to make a recursive call on null. Node not equal to null is now false. We're going to skip the conditional code block, which means we're doing nothing at all. And this code block is going to return and do effectively nothing. And this is where things get, my mind keeps going to tricky. Not tricky, but this is where we start seeing the power of recursion. There's going to be a theme throughout this whole memory diagram. This node this stack frame right here, it added a stack frame to the stack, so it's no longer the active stack frame. This stack frame then returned, it popped off the stack, and now this stack frame is at the top of the stack again, meaning it's the active stack frame again. And the question we have for the stack frame is, now that you have control again, what are you going to do? And this stack frame remembers, all these stack frames remember where they were when they gave up control, when they added a new stack frame to the top of the stack. This stack frame remembered that it just made its left recursive call. So once it gets control again, it knows to go on to the next line. It remembers where it was in its execution. It was waiting for this to resolve. It has control again, so that resolved, and it's ready to go on to the next line and make its right recursive call. Makes its right recursive call, which is again null. So that stack frame doesn't do anything. It just pops off the stack and gives control back to this node again. And now this node has control for the third time. It's going to know that it was waiting for this recursive call to return. So now that that recursive call is returned, now it can go on to the next line of code and execute this print line and actually print its value to the screen. So each node, each stack frame we're going to see is going to have control. It's going to be the top of the stack, the active stack frame, 3 separate times. The first time it's going to make the left recursive call, second time right recursive call, then third time print its value and return control back to whatever stack frame called it. So that stack frame's done. It was able to print its node. It pops off the stack, and then this stack frame is on the top of the stack again. It gets control again. It remembers that it was making this recursive call, So now it must be ready for its right recursive call. So it can make that right recursive call. Node dot right is 480. Make that recursive call, which is going to start the process over again over on the right side. That recursive call, not null. Node is not null. So make its left recursive call. Dot left. Make that recursive call, which is not null. It's going to make its left recursive call on null. That returns, this stack frame remembers that it was making this call, so it's ready to make the right recursive call, which is also null. And at this point, I want to slow down a sec. I don't have a ton of time to slow down, but we've got 2 minutes. We can stay on this slide for the rest of the lecture. And this is as complicated as this recursive call is going to get. So let's digest this a little bit here. We have 4 recursive calls on the frame, plus the main stack frame. We got 5 stack frames on the stack. And these stack frames are all remembering where they are. Well, the active one is currently running code. But these 3 stack frames all remember what they were doing when they had control last. And they're going to remember through something called a program oh my goodness, my brain. Program pointer? Program counter, I thought. Anyway, it's a 220 topic. They'll tell you the right term there. And each one of these remembers when it gets control back, what's it going to do next. And this is, if you're trying to not use recursion, this is what you would have to code. All this information of every node, any arbitrary number of nodes, remembering where they are in their computation. So this stack frame here is waiting right here for its right recursive call to end. This stack frame, when it gets control, it's waiting for this left recursive call to end. So next time it gets control, it's going to run its right recursive call. And this stack frame is waiting for its right recursive call. So when it gets control again, it's going to print to the screen and then return. So we have all these stack frames remembering where they're at in the execution of the program and ready to do the next thing once they get control again. Any quick questions about this? And then all these stack frames do end. This one doesn't do anything. Gets control again, which is going to print to the screen. It was waiting for its right recursive call. So it's printing to the screen and returning. Gives control back to this node, which just made its left recursive call. So it's going to make its right recursive call on null, which does nothing. Returns. This stack frame gets control again,